For the moment being, let's state, so we had now the model approach, we had the practical approach, and both state, of course, yeah, we live in this cyber-physical world. And it's not only about the timing, it's also about the mass of information. We talk about big data, we talk about complexity of the problem. And the question is now really when we advance those things into the future, so is it enough really to just stay with the models that we have, just more or less focus on developing new tools, on systems, or do we also maybe need to catch up in our thinking in terms of strategy to cope with all this information? Professor Myrtus, what is your opinion?
Yeah, I think it's a combination of automated, autonomous computer systems and humans. So you cannot avoid that sort of mix.
Yeah, that's what I thought. So then we are looking forward to hear your presentation.
Thank you.
Yeah.
If you think of the situation awareness, then there are two different situation awarenesses. One is for humans, another one is for non-humans. They're both intelligent, maybe intelligent, maybe not equally intelligent, and they, in many cases, they cooperate. They have a common goal. So what I would like to discuss, or to speculate rather, is my experience obtained from 2 or 3 different projects. Some of them ongoing, heavily ongoing, some of them not really related to situation awareness, but just the behavior of autonomous networked computer systems. And to my mind, we shouldn't stress specifically that cyber-physical systems and humans. I've been the believer that cyber-physical system has always had humans in the loop, not just supervising, but in the loop. It comes back to the moment when the first embedded computer system was developed in 1957, I think, in the chemical industry. Now, if you think why accidents happen in nuclear power stations, in chemical factories, they usually happen because of the outdated situation awareness. The operator has a huge panel with information on it, and when something goes wrong, there is a shower of alarms, and the network slows down, and the operator gives a mix of data which belong to different time instants, and he gets not true situation awareness, and then he amplifies the situation by making wrong decisions. So we shouldn't believe researchers who keep telling that the situation awareness is a snapshot. You take it and you use it for some time. It's always a question, how long can you use it? Well, anyway, I'll go through some of the, I think, trends in system development. I say a couple of words about distributed computing compared with cloud computing and fog computing, and then compare slightly situation awareness for humans and for other autonomous components. And I conclude my talk with what I think might be a rescue in the future. That we build autonomous computer systems with a self-aware architecture, since this event is devoted to architecture anyway. Self-aware architecture is not very intelligent but good enough human being inbuilt into technical devices and in the network. Each node has its own clever man, and they keep an eye on the situation awareness and they consult, because situation awareness is individual situation awareness and group situation awareness. And the problem, research problem, is really difficult for the group situation awareness. Okay. Some of the ongoing changes that I think it's a collaboration of autonomous software-intensive artifacts and humans as equal partners increases. I'd stress that they are equal partners. Humans are not supervisors, they are not bosses, they're just part of it, and quite often the weak part of the system. They should be handled with care. Second trend is that the role of ad hoc networks increases. If you think of the Internet of Things or social networks, they are kind of ad hoc networks. If we look at the papers and research going on in computer science and in cyber defense, they are mostly in ideal conditions, in the hardwired networks with a perfect access to any place, no disruptions in the communication. This period has been over for many years already. If you look at systems that are defense-oriented or should be working in the field. And increasingly, whenever you have ad hoc networks, the communication there will always be intermittent. That's the second problem. Then the third one is that collaboration of heterogeneous autonomous networks becomes a necessity. You cannot imagine one huge worldwide internet and that's it. Usually the problem is that you have hundreds or tens at least autonomous small-scale internets which still are connected to each other and cooperate, and that makes the analysis of a global network much more difficult. Next trend is that the role of humans in forming and spreading situation awareness will diminish, because the systems will be more and more based on autonomous computer systems. And as you know, in many cases, humans just cannot physically stand the load. Take the fighter planes, for example, the pilot will lose conscious every now and then, depending on how he flies, of course, but depending on the pilot. So you must start to trust the situation awareness provided by autonomous computing systems. And the next one is that the importance of group situation increases, which is the mystical problem. Humans have not solved it for social groups. That's why politicians always keep arguing with each other. They cannot form a common situation awareness. And majority of systems exhibit emergent behavior, which I have not heard of being talked here. Emergent behavior is a kind of a behavior in a system which cannot be deduced theoretically, logically, whatever means, from the actual structure or topology of your system or the algorithms that you apply in a system. It's because of the factors that you have neglected when you design your system. That's part of the complex systems. That's a essential part that actually causes complexity of systems. So it's an example of a traditional system of systems which is used for providing situation awareness for different missions. It's one of the systems called MAGIC 2. As you can see, it has several huge databases. It's even worse. These databases are in different countries. They have to follow rules that are different in different countries. And they are, when you are on a mission now and you need information from different databases, where is everything written down, maybe slightly outdated, but still, then you need the perfect communication ability, which you never have. And when you are in mission flying, for example, or driving a car or any other vehicle, then you might be in problem. It's one part of this huge picture. It's an example of a ad hoc network which contains or comprises of several active and passive sensors and UAVs and whatever other systems you have, the battle management systems, which are usually autonomous, have autonomous system of sensors and information, etc. And the sensor doesn't mean what it used to mean, that it's just a sensing element that takes a reading or transfers the phenomenon or physical feature of a natural process to electrical or whatever signal. It is a small cyber-physical system. It has sensors, it has processing power, it has batteries, it has a communication part. So they are autonomous cyber-physical systems. In the most cases, they don't have humans in it, but whenever you now connect those sensors or sensor information after being checked and put on, for example, on a special layer on a digital map, then you can start distributing it to the warriors or to the headquarters or to different users in the field. And then, of course, it becomes more important. Now, cloud. Everybody speaks today already about cloud computing. Even politicians have learned this. They mention cloud computing much more frequently than cyber defense. Have you noticed that? And it's fantastic because it's a distributed infrastructure. Sorry, it's instead of distributed infrastructure, it's a converged infrastructure. You converge all the infrastructure and services into cloud, which is nice. The difficulty is that, again, when you are not in the cloud, but somewhere under the cloud, on the surface, you need a good communication to the cloud. That's the first thing. Second thing is that it's a huge arrays of data. It's a big data that you collect via sensors or via ISR or from the OSINT or due to human information. It's a huge amount of information and you need huge bandwidth to load it up to the cloud to be sorted and processed and whatever is being done there. That it's not very realistic. So to fight with this, people have started to talk about fog computing. Fog is a cloud which is very, very low flying. Or mist computing even, which means that you actually do processing at the spot where you get the information, whenever possible. And it is possible nowadays because each of these smart sensors with a processor and radio receiver and sender has computing power of a typical laptop. Well, maybe less, a little bit less, in some cases at least. But still, if you now think of sending a spectrum of acoustic signal when you have an array of microphones to locate moving object or identify and locate the moving object, and you process the information on the spot and send just the answer. There's a huge difference. Now, this leads me to the problem that when you have the fog computing or mist computing, you need very efficient communication between smaller areas. And that is provided by proactive middleware, which is a key to efficient fog computing. It's based on the idea of subscription to data. The consumers will subscribe to certain data, and they never know where this data comes. But the middleware has to look it for this data. You have automatically checked the validity time of the information, validity of time and location, plus the usability period of that information. That can be checked by proactive middleware, and you have validity requirements dynamically defined by the consumer. When you subscribe to information, you say what sort of data you need. That avoids or guarantees efficient use of the bandwidth. So that's an example of a proactive middleware. You have several agents. When I say agent, I don't make difference between the humans and devices. In each case, for example, if you exchange information via digital map, then it's just in the form. If you send the information to the computer, you needn't give a full map with it. You just send the appropriate data structure. If you send information to human, you have to include the background map as well. That's a more detailed fragment of a proactive middleware. You see that each agent there has a specific interface to the middleware. It's very much the same system as a Corba middleware once was developed. But it has intelligence in it. Which leads us to the possibilities of verifying the systems automatically or forming the situation awareness automatically. It's typical in self-organizing multi-agent systems that you have autonomous interacting components which exhibit cognitive and proactive behavior, which is susceptible to situation constraints, temporal, spatial, cultural, social, etc. And there is no difference whether they are computers or humans. There have been studies which compare the traffic forming in a mobile network, mobile telephone network, and in a ad hoc network of autonomous computing systems. The pattern of traffic that develops is very much the same, because autonomous computing systems talk to each other. They make commitments, they make contracts, they make order data, they receive data, they send data. It's quite amazing how similar are the behavior of a bunch of computers and a bunch of humans. No insult to humans.
We are a bit behind schedule. I just have to push you a little bit, seeing it
Okay.
you're at slide 9.
I'll see it in 5 minutes.
Yeah.
You want me faster? Okay.
No, just...
Then we need to keep systems behavior within a security envelope, and as soon as you modify, the self-organizing system modifies its behavior, you would be interested in actually making sure that it still satisfies your requirements, which means that you need a theory for dynamic online verification of behavior. It's fostered by shared situation awareness of components, supported by well-defined direct interaction, indirect interactions, and mediated interaction. And now I don't want to mess you up. These are the mathematical background of the mediated interaction, but the trick is that mediated information enables a pretty nice application in a cyber defense. If you build into each network node, into each router, into each server, mediated interactions, which enable you to monitor what's going on, which enables you to censor all the traffic that goes through, then you can detect unusual behavior pretty quickly. And you can also pretty quickly block it. No problem, whether by humans or by whatever, computers. And that's basically all I wanted to tell.
Yeah. Quick question for Professor Murtos. Actually, I have one for you, and at the same time also for our subject matter expert. And now that we are aware of the self-aware systems, so I already asked the question about artificial intelligence, so full AI and more or less aware systems, so there is a little gap in between. Will such a system be able to, first of all, identify user mistakes, or even maybe user sabotage, manipulation of the system?
In principle, yes.
Yeah.
It's not very much difficult. It has been used, this kind of a self-aware architecture has been used for simulation of swarm intelligence in many cases, and you can actually simulate and understand why a swarm or a flock of birds flies like they do, and what kind of communication they do. And
so can we use such a system also for insider threat detection in such a scenario? This question goes to Mauno.
Well, yes, definitely, because such a system would allow us to handle huge amounts of data much faster and making better use of the bandwidth and system resources and extracting knowledge in a more efficient and smarter way.
As a hot wrap-up and for a final statement of the panelists, so seeing situational awareness of tomorrow, so what needs to be the focus now of development and research? If you would comment, Gabriel, and then all of the panelists.
I think we have to make a difference between kind of something that we like to get answered, just a curiosity. And the second part is we want to resolve problems. I think in terms of exploring the world, there are plenty of issues that we need to attack, but I would like to concentrate problem resolution. And the problem resolution is scalability. The issue is effectiveness. And the third issue is believability. You know, it's not only important to get answer, but the user, consumer of our results should have a trust. So the trustability, believability, and also intelligence system should be able to explain it. So explainability. So I think these are the critical issues.
Thank you. Dr. Töller?
I talked about so many different challenges that it is now really hard to decide on the one perfectly to the one challenge which has to be managed first. So I would say the best is to work strongly together with the operators of systems to develop existing systems further and further, to learn what the real practical needs are, and to improve the systems that are out now.
Okay, thank you. Professor Mötos, what's our way ahead?
Well, I dream of a future where we will not actually neglect the cleverness of the computers, and where we do not overestimate the intelligence of humans.
Okay.
Because intelligence comes with physical fitness, and humans are not physically fit for the many systems.
We will actually elaborate a little bit more on this in tomorrow's AI session, which I actually want to invite you to join, because we will actually catch up exactly with this argument. And yeah, let's be surprised, just a little bit of mouth-watering for it. Mauno, do we agree with those proposals?
Yes, exactly. And I just want to say that I was really pleased to see that all the presentations actually outlined what we have discussed in different groups and also in the university. And I specifically agree with Dr. Töller here, and well, and something that even Admiral Rogers said this morning, that we should really come up with a common understanding of situational awareness, and agree on common symbology, and so everyone would be able to understand what is being presented to them in a quicker and more efficient way.
Okay, thank you. Any more questions from the audience? I know, it's coffee time. No worries. Then thank you to the panel. Thank you, Dr. Gilson. And of course, for you as well, we have the nice speaker gift. Thank you. Thank you, Professor Mötos.
My pleasure.
And thanks, Mauno. For you.
Oh, thank you.
That's for for the subject matter expert. Gets a chocolate bar. Okay. One more administrative remark, since we ran a little bit behind the schedule now. So let's start the follow-up session.